Okay, so today what we're going to do is continue talking about series and like more criteria for convergence. So basically, the plan for like the upcoming weeks is that I by this week we should wrap up everything related to series, like how do you test for convergence or divergence, and then after like next week we'll start talking about power series, which is actually one of the nicer topics of the course. That is like a really like useful topic. So, but yeah, like we just have to like finish saying some stuff related to series, more about series. And just for those who just came, I was saying that like there's no quiz on Thursday during recitation because today is really like the first day we're discussing new things after the exam. So there still will be a workshop and everything, but yeah, no quiz. Okay. Sorry, yes. It is not cumulative, but like you are welcome to use whatever was required from the second exam. Like the thing is, like at least with some of these topics, like they do, it's hard to forget, like what you just learned because it is reused very often. But it's not that there would be like a question specifically. There won't be any questions that I would just have been able to write on the second exam, especially because, again, now that we move with this power, like the next topics about power series, stereo series, like these other, like you just have so many things to ask from there. The final will be cumulative, but like not the third exam. Although like again, like there might be a few things that you would need to know about that. Yeah. So because we're the honors section, it may be that we have like a slightly wiggle room in that maybe like 90% of the problems like would be the same as like those like of the remaining sections, but like or I'll have to figure that out. But it may be slightly different, but not you know not by a significant amount. You should still think about it as a cumulative final and all the stuff. But it definitely would happen, like all the Calc 2 exams do happen at the same time, same day, which actually I think I already have like that information. I can send you like an announcement with where like it would take place. But yeah, like there might be like what you like a tiny variation, but I do have to double check that because I'm not super sure. Um, Okay, so the first topic that I wanted to tell you about today is what's called like absolute convergence. And here, when it says the word absolute, you should think about an absolute value. So that's what you should keep in mind. So here, like, keep in mind absolute value. Okay, so the idea is like, say you have like like a regular series, like a normal series. So if you have a series. By the way, usually I start, I think I've said this before. I usually start the series at one, like k equals one. There's nothing really too special about that. You could have started at a k equals zero, or you can start it at any other like finite value. But sometimes it's convenient just to start them at one. But if you have a series, you say that the series converges absolutely. Like if the series where like each of these numbers is replaced by their absolute value converges. Okay, so. If so, just to emphasize what we're doing, we're just putting absolute values to each of the numbers that we are adding up together. So basically what I'm doing is replacing each term of the series with its absolute value. Okay. Or taking up the absolute value of each term of the series. So before like mentioning why this is like a useful concept, let me give you like some examples like of like absolute convergence and others where it does not occur. So let's do. So if you take a series like this one, like -1 to the k over k squared. So I can write some like of the initial terms first. So it's like -1 plus 1 over 2 squared minus 1 over 3 squared plus 1 over 4 squared minus 1 over 5 squared, right? Plus 1 over 6 squared, and it continues, right? So essentially, it's the reciprocals of like the squares of integers, but like now you're like alternating the signs, right? Like plus, like, well, it starts with minus, minus, plus, minus, plus, minus, plus, minus, plus, right? So this series converges absolutely because what happens if you take, so if you want to know if a series has absolute convergence or not, what you do is consider like the absolute values of like these terms. Like, so basically, you just like make them all positive, which is what taking absolute values means. So and if you remember, like this series, it converges like it's kind of like a comparison test with like an integral, right? Like, and it's kind of like a p equals two like test. So this one like converges. Like for example, you could compare, for example, compare with like. Sorry, let me go. Oops. Yes, sorry. Mm-hmm. Oh, you mean this k? The thing is like -1 to the k, that is plus or minus one, right? The absolute value just turns all those minus ones into plus ones, right? So there's no more like, like essentially like that's why it's maybe better to look at it like from like the first few summoned, right? Because if you look at the first two commas, like you're just doing like the absolute value of this, the absolute value of this, the absolute value of this, right? And then all the minuses go away. But once the minuses go away, the only thing, you don't have like any use anymore for like the numerator, if that makes sense. Like all the numerators become one, right? Because the absolute value, it is kind of like, I mean, this is just like a clever way of writing one or negative one, right? Like, but that is essentially all that it is. So that's why they all kind of become one. Is that making sense? Okay, so and again, I still haven't said why this is useful, but for this particular series, you would say that there's absolute convergence because if you take the absolute values of the terms, you get like a convergent series. Okay. Now here's one that does not converge absolutely. So here's another example. So if you take so instead of like k squared, imagine I had just done k. Okay, so that would be -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus 1/6 dot 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 dot. So instead of like squaring the integers like in the denominator, I just keep them as they are. And now say I give you the series and I want to know, does this one converge absolutely or not? And this one does not. Since what happens if you take absolute values of the terms? Again, like the only effect of the absolute value here is like to make all the numerators identical to one. So you just get this series, which if you remember, I hopefully I mentioned the name for it. It's called the harmonic series. So like this one diverges. In fact, like you could do like a comparison with like the integral of 1/x dx, right? So this was like the harmonic series, like a famous one. And this one diverges, okay? And again, like if you forgot about that, you still can do like comparison with an integral. Like example, compare with an integral. That is kind of like the easiest way to see that this one is supposed to diverge. Yeah. Oh, so right, like that's what I was. Yes, this is the next step, right? Why am I talking about like absolute convergence? So the idea is that I'm about to write this, but if the series converges absolutely, that forces convergence of the original series. If the series does not converge absolutely, anything can go. So maybe the original one converges or like the original one diverges, but you cannot tell. Like I'm going, sorry, were you going to ask me something? Uh-huh. Right, it's kind of like a way of like kind of like it many times it's like a two-step process because the idea is like you're trying to test if a series converges or not. Sometimes it's easier to not work with the negative numbers because then you can do a comparison. So you take the absolute values, and if you happen to be lucky and it converges after taking absolute values, you're good to go because the original one would converge. So it's kind of like the idea is to use it eventually for a comparison test, either with a series or with an integral. Yes, sir.
Say just say that you're just absolute, just that data
No, like then it could be whatever, then it doesn't help you at all. Like it's kind of like agnostic, like you don't know what happens. Like there will be examples where, it doesn't I'm actually going to write some like in a moment, but yeah, like if with absolute values it diverges, you cannot tell anything about the original series. So I'm going to like do examples of everything. So but yeah, like let me I have said already some of these things, but why is this useful? So why do we care about absolute convergence? About so as I was saying, the idea is that if the series happens to converge absolutely, then that forces convergence of the original series. So convergence, then the original series will converge as well. Like, and actually, let me write the symbol for the original series. So the original series was like without the absolute values, right? However, again, that's all that it's saying. So if the series with absolute values diverges, that doesn't tell you anything about the original series. So like like this is not like a useful thing in that case. And I'll kind of give an example of everything. However, if the series with absolute values diverges, then the original one could converge or diverge. Like that depends on the specifics of the series. Yes.
This is because summation of, I guess, like after y is NK is always going to be greater than the summation of.
Right. Like the intuitive actually was going to write kind of like an intuitive idea, but it's what you're saying because if you make everything absolute, right, like everything is positive, so everything kind of adds up in the same direction, right? Whereas if you have things which are positive and negative, like there can be more cancellations going on, and so like that kind of like shrinks like the value of the sum in a sense. That's kind of like the idea behind it. I mean, you can make it more precise, but it's kind of like plausible enough, right? Because like if you are just adding positive stuff, then like the sum just increases. And so if that is finite, that kind of like forces the thing with like that fluctuates, the plus minus, like or like plus minus, like to be finite as well. Yeah. So that's oh so yes, were you going to ask me? I mean, like, it's kind of one of those things that uh you develop a feeling for, right? But like, you kind of like think, okay, like most of these things, like it's not that when you have like a series, in most of the cases, it's not too bad to kind of like figure out how it would look with absolute values. And then you can do like a quick check of, does it look like convergent or not? Like, but right, like on the absolute, like, I mean, on the exam, there could be like a problem that says explicitly, does this converge absolute? Like, but like, the thing is like by the end of, like this week, there will be tons of like different tests that you could use for like trying convergence or divergence of series. And then if you're not asked for a specific method, then you're free to try whichever. So the thing about series, which is kind of like fun, is that many times like you can there are like 3 or 4 tests that work on the exact same series. It's not that there's only one way to do it. So there's about a lot of flexibility when it comes to determining whether the series diverges or converges. So unless you're kind of like asked for a specific approach, like you could again like even do integral tests, which was like officially on the second exam for like example. But yeah, like there might be like a problem that is just like does it, like literally converge, does this converge absolutely or not? But if not, like you would just like maybe test it out. But yeah, like maybe before continuing with the examples, uh, the intuitive idea is that it should be harder to, if all the terms are positive, it should be harder to get like a finite number because all like the contributions like add up. There are no cancellations. That's kind of like the idea behind it. If you read the book, if you're interested, like they kind of give like an argument, but it's not, that different from what I just said. Like, so like the intuitive idea is that it should be harder for like the series with absolute values to be finite, since all the contributions kind of like add up in the same direction, right? Since it just the partial sums keep getting larger and larger, keep increasing, given that there are no cancellations. That can occur when like like the sequence has like positive and negative numbers. You are adding positive and negative numbers. Is that okay? So just to kind of like let's go back to those examples that I started with earlier. So what does that tell you? So for example, back to back to our examples. So I had said I think this is the first one that I did. I had mentioned that the first one, right, like the reciprocals, like of 1 over an integer squared with like alternating sign. This one did converge absolutely, right? What we just said tells you for free that then the one with alternating signs converges as well. It's kind of like free convergence. That's how you should think about it. Yes. It is like a similar idea to like a comparison. I mean, in fact, if you were to read the proof on the book, it essentially boils down to doing like a comparison of sorts. Yeah, yeah. You kind of break the sum into the partial sum into a sum of like the positive terms minus a sum of the negative terms, and you kind of like each of those pieces has to on their own converge by comparison, and then like that forces like the convergence of like the difference of those two. Yeah, yeah, it's not too bad, but it's also like not worth, like, I feel like can be like omitted from like the class just because like the idea. But yeah, it's kind of like all the convergence, kind of like every convergence thing is a comparison at the end of the day. Like if you kind of were to dig further, like there's almost nothing else that you can do besides comparing. It's just there are more clever ways to comparing than others. But yeah, like almost every convergence test will be like a comparison secretly to something else. Um, but yeah, it's kind of like a comparison test. Yeah, yeah. You should. Okay. Um, Okay, so this is an example where we got like the convergence are free. And then what I was saying is that if the series does not converge absolutely, then you don't know anything. So just to continue, so this was the first one. Then the other one that I had said is that so I had mentioned, right, that this series does not converge absolutely, but this one does happen to converge. Like, and we'll see that later. It's called like there's I don't think I'll do it today, but definitely on Wednesday. There's something called like the alternating test that will tell you that like a series like this will converge. But we will see by other means that it does converge. We'll see later. Okay. So this is an example where there's no absolute convergence, but there's still convergence. But then there are also examples where there's no absolute convergence and there's also no convergence. So like that shows you that both options could happen. And so here's an easy one. Here's another one. If you just do -1 to the k, right? Okay, so this is what it is. -1 plus 1, -1, like -1 plus 1, -1 plus 1, -1 plus 1, right? So it's -1 plus 1, -1 plus 1, -1 plus 1, -1 plus 1, blah, 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 for eternity. Definitely, if you just put absolute values here, like this blows up, right? Like it's just 1 plus 1, 1 plus 1 plus 1 plus 1 plus 1 plus 1. So there's no chance that this one converges absolutely. Does not. Absolutely. Again, if you put like absolute values here, like, oh, like you just get ones. And that is kind of like the most, like, very clearly like divergent. Right? But also like the original series, but in this case, the original series diverges as well. And like, for example, you could do like the nth term test because like the terms that you're adding do not go to zero, right? So, and also the divergent, and also the original series, also in this case, without the absolute values, diverges as well. and term test. Because if you look at the partial sums, sometimes they're zero, sometimes they're depending on how many terms you're adding, like -1 or things like that. Yeah. Oh no, but the thing is like there's a summation symbol, right? So you're adding a bunch of ones, which is what I'm putting here, right? So if you look at the partial sums, like first is one, then you have a two, then three, then four, then like the values of yeah, like the right? Like this is if you only had like the sequence, yeah, it's like a constant sequence, but you're adding the terms of that constant sequence, so you just keep growing. Yeah, yeah. Right. So there's always like a difference between convergence of the sequence that you're adding versus convergence of like the sums that you're getting by adding those like terms. Yeah, yeah. Yeah.
Is also divergent.
Yeah. Also for like here I wrote like nth term test, right? Because if you remember like for a convergence series, like these terms need to go to zero as n goes to infinity, and like the terms are -1 plus 1, -1 plus 1, -1 plus 1, right? So that is one way to see it. Another way to see it, if you wanted to do it more like empirically, right? You just look at what the partial sums should be, right? So I'll do it quickly on the board because what are we doing? Like we're doing -1, -1 plus 1, -1 plus 1 minus 1, right? I'll just do 4 because like that kind of gives you like a feeling of what happened. So like the first partial sum would just be -1, right? The second partial sum would be 0, but like the third partial sum would be -1, right? Then the fourth partial sum would be 0. So like the partial sums are always flipping between -1 and 0 depending on how many terms like you're adding. So there's no, they will always kind of like go back and forth between -1 and 0. So there's no like a specific number that they're convergent to. But you don't have to, I mean, you don't have to do that directly. You can just have to say like each of like these individual sums is not going to 0 on that limit. Is that making sense? Any other questions? Okay, so just to kind of like throw in some like terminology from logic. So if in the world of series, if you have ever seen like these Venn diagrams or things like that, so there's the island of series. If you if you choose a point on this island, you get a series. On the island, there's a smaller island, which is like the world of all convergent series, right? And inside the world of convergent series, there's the world of series that absolutely converge, okay? What that means is that the moment that you are in this island, you know for sure that you're in the bigger island. So that's a way of saying that the moment you know that you're absolutely convergent, you know that you're convergent in the regular sense. But not everyone who is convergent converges absolutely. So one way to say this, like if you want, like just again to throw in some terminology, is that it's absolute convergence is sufficient for regular convergence, but it's not necessary. Like it doesn't need to happen. It just suffices. Like if you know that it occurs, like you get convergence for free. So um, so being absolutely convergent is sufficient, but not necessary for regular convergence. So again, like that you, not that we need this, but like if you ever need to take something like discrete math or whatever, if you call P being absolutely convergent and Q being like regularly convergent, then this is kind of like you would write as P implies Q, like absolute convergence implies regular convergence. So just kind of like if you call P absolute convergence, and Q regular convergence, then like in logic or like mathematics, like like in logic, usually you would just write this as P implies Q. Which this is a way of saying that whenever P occurs, Q is supposed to occur, like but Q can occur without P like occurring. But that's just another way to think about it. Like probably the island picture is like the Venn diagram is more simple to understand. Um, so like being absolutely convergent is kind of like an extra special condition, like yeah, is that okay? Making sense so far so good. Okay, and then at least for like the remaining minutes, there's like a way to test for absolute convergence, which is called the ratio test. So it's really cool. So like I'll tell you about that in like the rest of the time that we have for today. So uh, the ratio test. So you should think about this as a test for absolute convergence. So what's the idea here? You have a series. So you have a series. And you want it to determine whether the series converges absolutely or not. So the idea of like the ratio test, what you do in the ratio test is just to like it's called a ratio test because literally you're going to take some ratios. So you take ratios of like the two consecutive terms that you're adding. So for the ratio test, you consider So, like, this is like the nth plus one term divided by the nth term, so like there are two, like, the terms that come together in the series. And then look at the limit as n goes to infinity of this ratio. Okay, so there are three, like, there are three things that can happen here. If this ratio, if the limit of this ratio is less than one, um, what does, what does it mean for, I mean, let's think about it for a ratio first, like, before, like, ignore limits for a moment. Like, if you have a ratio, right? If you have a ratio which is less than one, that means that the numerator has to be less than the denominator, right? I hear everything is possible, right? Like, so there's no way worry about flipping inequalities or something like that. So what the ratio test is like says is that if this limit happens to be less than one, well, you should think about it. What they're saying is that the terms, the successive terms are getting smaller than the previous terms, right? So everything is kind of like shrinking in terms of like what you're adding. And in fact, what the ratio test current, the series converges absolutely. So I'll write that down. So so option one, which is like the best case scenario. So option one is that if then the series converges absolutely. Yeah.
Say that the series with the absolute value converges absolutely.
Oh, sorry. I mean uh right. There's no difference. Like the series with absolute values and without absolute values both would converge, because if this one converges absolutely, that means that both are convergent, right? So I'll put that into parentheses just to clarify, so that both in this case would be convergent. So yeah, that's kind of like thanks for like yeah, like so both with or without absolute values, they're convergent. Which would be great, because this is kind of like the best you could ask for. Like, absolute convergence is kind of like the best convergence in a sense, because it's the hardest to get in some way. Um, then option two, what is option two? For this ratio to have a limit that is greater than one. Okay, so let's think about what happens in that case. And again, it's kind of like useful, oops, sorry about that. It's kind of useful to just think about it with before like writing everything down, just with a single ratio. So if you have a fraction, right, which is which is greater than one, what does that mean? That means now that the numerator is greater than the denominator, right? So here, when you look at consecutive terms, you are making the numerator larger than the previous term. So like you have like, like that means that like the fifth term is greater than the fourth term, and the seventh term is greater than the sixth term, and the 10th term is greater than the ninth term. And so actually like the terms of the series are that you're adding keeps growing and growing. So here what you would expect is for everything to diverge. There's no way to get convergence here because you're actually making bigger what you're adding into the series. Yes.
Doesn't the harmonic series isn't the harmonic series ratio also always less than one, but it doesn't converge?
No, it's actually exactly one.
Yeah.
Yeah, we'll do it. Actually, we'll do that one. Like,
Okay.
yeah, no.
Okay.
That's a great question. It is literally one.
Oh,
No,
limit as
this is strictly great.
infinity as n.
Yeah, yes, but no, that's a good one. Like, yeah, it will be literally one, and that's why you cannot say anything, and that's going to be option 3. Yeah. Oh, well,
Like, why don't we just state like a bunch of ratios like that's.
well, the thing is that you do want to, I mean, a series, a series is a sum of infinite terms, right? So to get a finite number, it really always depends on what's going on at the very end of the series, because you don't care about how the first 2 quadrillion terms behave. That's kind of like the same thing about infinity, right? Like a trillion is small compared to infinity. Any finite number is small compared to infinity, right? So like in the end, like if you want to understand whether convergence occurs or not, it really always has to do with what you call the tail, meaning like what's at the very end of the series in a sense. And that's what you have to take the limit as n goes to infinity, you see? Because it doesn't matter how the first 10 trillion ratios are behaving, if like that, you really care only of what's happening at the kind of very, very, very into the future in a sense, you know what I mean? I probably would just do the exam. I do want to do kind of like some examples today, and then because we don't have that much time, and then I'll do like a big mini explanation of what this works on Wednesday. But I think it's better to do like examples of each, so that you see kind of like it plays out. But it's kind of like the intuitive idea here is that each new when you have 2 terms, because this ratio is greater than 1, the terms are kind of getting larger than the previous one. So like the terms keep growing and you're adding them all together. So like you keep growing like what the sum is supposed to be. So that's kind of like what's happening secretly. So but in this case, so both series diverge, which is also nice. So it doesn't matter whether you had absolute values or not. So as you can see here, the first 2 options are kind of like the best worlds because you have like complete information about everything, like all the conversions that you could like ask for. And then the last possibility is like the one that doesn't give you anything useful, which is when this limit happens to be exactly 1 or does not exist, because that's also a possibility. No one says that the ratio has to have like a limit. So option 3, and I'll write one of each case. Is that if the limit of the ratios, if you remember, like the second derivative test in Calc 1 is kind of like inconclusive, like what you would call like the test is inconclusive because you cannot really say anything useful about it. Yes. Right, but this is not right, but this is like a special case because here something else, which is like the behavior of the ratios, right? So you have like extra information. Right, like in general, if the with absolute it is true. If with absolute values the series diverges, then still you could have convergence or divergence for the regular one. But you have like extra information in this case. The extra information is that the ratios are becoming greater than one. So it's not just like you have like that plus something else. You see, yeah. Because otherwise, I agree with what you were saying that like it doesn't tell you anything. But I'm assert like here I'm saying no, I actually have more info, which is like that these ratios are getting greater than one. Or does not exist, then like the test is useless. Like that's basically what nothing you can say. Like anything could happen, like. Okay. So I'll again, I still have, I feel enough time to at least do an example of each option now. And then next time I'll give you maybe like a 5-10 minute like idea of why this is supposed to work. It's still kind of like useful to understand, but it's better to just start with examples so that you see what's going on here. So you can say that the test is inconclusive, just by analogy with how you would call that on with the second derivative test. So, maybe there's absolute convergence, maybe there's not, like, maybe with absolute values it diverges, but without absolute values it converges, like, anything can happen. So like, if you get option 3, that, you didn't gain anything. So let me start with option 3 because like you brought up the harmonic one. So it's kind of like actually nice to see what happens with the harmonic in this case. So which is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, blah, 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 blah. Okay. So in this case, the nth term is just 1 over n, right? So here, a sub n is 1 over n, right? What is a sub n plus 1? Is 1 over n plus 1. You see, like, maybe it's becoming a bit more clear why the ratio will be 1. If you take the ratios, right? What is the ratio? Is an plus 1 divided by an. In principle, it's with absolute values here, it wouldn't make a difference because they're already all positive, but otherwise you would need to, you know, you would need to like, take absolute values. And then like, well, a fraction of a fraction, if you remember how that goes, you multiply kind of like the first numerator with the second denominator, and then the first denominator with the second numerator, right? And so you get this. And so we're looking at the limit as goes and n goes to infinity of this. Okay, one option is to do L'Hopital if you wanted to, totally fine. Other one is like they're polynomials of the same degree, right? So the limit is just the ratio of the leading coefficient. So it's 1 over 1, which is just 1. And so that you landed in the, case where it is actually inconclusive. So you would need other things to say whether this one would have been like divergent or convergent, So like, so this is like an example of option 3. So you cannot say anything based from the ratio test. So ratio test not useful. that okay? Is that making sense? Questions up to this point? Okay, so this is an example of where you landed in option 3. Now let me do an example for option 1. Did I already talk about the factorial or of a number, or I haven't? I'll bring it up. Okay, so just like because it's actually going to be useful, and maybe I'll just do this like, and then next time I'll do option 2 because I don't want to kind of like finish like on in a rush. So just as an aside, what is like the factorial of a number? It's usually easier to just like start with some examples. So 1 factorial is 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. Hopefully you see where the pattern is headed. 4 times 3 times 2 times 1, which is 24, right? I'll do one more. So 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. Okay, and as you can see here, like what is n factorial is the product of the first n integers, right? So n factorial is like n times n minus 1 times n minus 2, 2, up to 1. Okay, and if you kind of like recursive definitions, right? What one way to think about this is like n factorial is n times n minus 1 factorial also, if you think about it. You just multiply by an extra factor. A useful convention, which I cannot go in, like, don't have time to explain, but it is useful to just say that 0 factorial is 1, which looks odd because like maybe it would make more sense to make it 0, but like there's actually like a good reason for why you would call 0 factorial equals 1. Just think about it, that makes it like your life easier, but like there's like a better reason for that. Okay, and why do I want to talk about factorial? Because there's like a very nice series that you can build with a factorial, which and this is like only time that I'll start the series at 0, and that's why I wanted to talk about 0 factorial. But let's say that you wanted to know if k equals 0 to infinity of -1 to the k over k factorial, whether this converges or not. So again, it's useful to just like work out like a few terms. So if you put k equals 0, that would be 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial, dot, 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 dot. So it's kind of like the reciprocals of the factorials, like alternating them, right? Is that okay? Is that making sense, everyone? With me? So far, so good. Okay, so let's just look at the ratio test, because like we're talking about the ratio test, so that should work in this case. So what is an here? A sub n would be -1 to the n divided by n factorial. And again, you have to consider the ratio of the absolute value of an plus 1 divided by the absolute value of an. Okay, so that would be the absolute value. Okay, it's a fraction of a fraction again, and that will happen a lot of the times when you're dealing with with the ratio test. Well, so the first thing is like the absolute values make completely irrelevant the minus ones, right? Like the minus ones get completely deleted once you have absolute values. So like just to simplify this a little bit first, I'll just write that as 1 over n plus 1 factorial divided by 1 over n factorial. Let me give you a chance to calculate it. Okay, everyone with me so far so good. And then fraction of a fraction, same story as before. You multiply numerator with denominator, like these two, and then these two together. And so you get n factorial divided by n plus 1 factorial, right? And now here you can use the formula that I just mentioned, that n plus 1 factorial is n plus 1 times n factorial. So this is n factorial divided by n plus 1 times n factorial. So nice, like the factorials cancel out. So the ratio is 1 over n plus 1. Is that okay? So far so good, making sense? And we need to look at the limit as n goes to infinity of this ratio. So what is the limit as n goes to infinity of this ratio because of what we just did? Oops, sorry, let me go here. It would be the limit as n goes to infinity of 1 over n plus 1, which is 0. This is definitely less than 1, right? That's like the only thing that I cared. This ratio is less than 1. So what does that mean? That means that we landed on option 1 of like the ratio test. So this is option 1 of the ratio test. And so by the ratio test in option 1, what that says is that the original series with or without absolute values converges. But that's what the ratio test says. So yes. Is that okay? Is that making sense so far so good? Yes. Yes. Here. Oh, right. The thing is, like, if you look at the factorial, sorry, just to go back up for a second. You know, if you look at the factorial, like for example, what is 5 factorial? It's 5 times 4 factorial. So like it's and a factorial is kind of like the number times the previous factorial. Yeah. Is that making sense? And now, just to finish for today, the reason why I wanted to do this series is that there's actually, in general, you don't know the value for finding the value of a series is very hard. So you only care mostly whether it's finite or not. But these two numbers are really special. Like we'll see later, there's a way to find them. So these, the one with absolute values, well, like again, the absolute value just removes like the -1 to the k. This is actually the number e of e of e 2.71, whatever. So this is going to be e, and this one is going to be 1 over e. And we'll see that later once we talk about like the Taylor series. We'll see this later. So the number E, if someone wanted to know what is the number E, is 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial. So on. So that is what it is. Which is like a very nice way to like write E, because factorial goes to 0 very fast. I mean, 1 over n factorial shrinks super fast. N factorial is an immense number, actually. Like if you think about it, because you're multiplying the first n integers. So these fractions get close to 0 super fast. So like you can approximate E very quickly. You know, this 1 plus 1, that's 2. 1/2 is like 2.5. And then you keep adding, like you almost get to 2.71 like in no time. So like that is like a very cool approximation. But again, I'll explain later why that works, but let's just finish here. And so next time I'll do like an example of option 2 for the ratio test, and I'll also give you like an idea of why the ratio test works. And as I was saying, at a minimum, I'll post the grades today for the exam. I'll try to release them, but I'll just check with the coordinator if I can do that. But let me just stop here. Oh, yes, let me just stop the recording.